Okay, well, I hope everyone had a enjoyable time at the symposium. I saw a lot of the faces there, so hopefully you guys learned a little bit about what everyone is working on. Hopefully you don't have to drastically change your faculty priority list for research projects. You'd usually like to try and get the symposium, well, last year we did it, in September, and so everyone had, all the first year students had a chance to see everything, but I guess we didn't quite have our act together this year. Hopefully it was helpful. Today we're going to talk about flash calculations. Now, from an undergraduate chemical engineering perspective, flash calculation is oftentimes specifically referring to a vapor-liquid unit operation process, where traditionally you have a feed that is generally going to be a liquid because if you can, you want to transport fluids. Me personally, I would much rather carry around a glass of water than some sort of pressurized gas canister or balloon. Now it's even worse when you have pipelines. Compressors are extremely expensive. I don't remember the statistics, but I want to say something that, a relatively large fraction of all power consumption in a chemical plant is consumed by either the distillation column or the compressors, right? So on some processes it can be 20-30% of the total energy costs. So if you can, you'd like it to be liquid. You then flash the liquid at some defined temperature and pressure where you're operating your unit operation. You're going to get some composition coming out of your vapor phase with a total quantity given by V, either the mass flow rate or typically the molar flow rate is because that's what we use to do the calculations. And then coming out of the bottom stream, we're going to be having, a liquid composition and a liquid flow rate, where L, in this case, or V, would be moles of vapor per second, or whatever other units you'd like to prefer to have. These two streams are going to be in equilibrium. So the bulk of this calculation is in the fluid phase equilibrium part, right? The total quantity of each phase is done after the fact using a material balance, where if I have so let's say it's an I balance for species I, the total amount in the system, in equals out, mass can't be created or destroyed if there's no reactions, which we're going to assume in just a simple separation process, moles aren't created or destroyed. So everything flowing into the system of species I is going to be the total composition times by the molar flow rate of the feed, which is going to be equal to how much is lost in the liquid stream plus how much is lost in the vapor stream. So this is what conventionally we refer to when we talk about a flash drum, because a majority of what we'll do as chemical engineers is vapor-liquid transitions. But generally, a flash calculation is any phase equilibrium calculation where you determine the compositions and quantities of each of the two phases. So a flash calculation could be solid liquid, it could be vapor liquid, it could be liquid liquid. We typically think of it, though, as chemical engineers as this unit operation. So to talk about a flash calculation, I'd like to reintroduce some more of these phase diagrams. In this case, today we'll talk about the PXY. In the handout I gave you, what is it here? Methanol and pentanol. So in this case, we're looking at the pressure as a function of the total composition. If I replicate the figure here, in the methanol and pentanol mixture, which one of these is more volatile? Just from intuition, right? Methanol is small, pentanol is big. 5 carbons versus 1 carbon. So we should know that the methanol is going to be the more volatile one. So we'll write that on the x-axis, and then we can confirm that is the case because at the fixed temperature, in this case this diagram is 90 degrees Celsius, meaning I've got a container at 90 degrees, I'm varying the pressure. The methanol has the higher saturation pressure. In this case, it's 251. 251 kilopascals. And the pentanol is down here at 15.3 kilopascals. We have two lines Now I'm not gonna, on the diagram I have them labeled, but we're not gonna label it for right now, just because most of the times in the real world, there will not be labels on phase diagrams ever. So we're just gonna live without it. Okay, that's better. So we've come across a phase diagram. We're talking about a PXY. So we're varying the pressure, we're varying the composition, but the temperature is fixed. What phase are we in here? Liquid. High pressure at a fixed temperature will condense us into the liquid phase. When I lower the pressure, the more volatile species will start to boil first, which is the methanol, which is 100% methanol over here. This is 100% pentanol down here. It takes a significantly lower pressure to boil pentanol. So that means down here we have our vapor, and here we have our two-phase region. Liquid to two-phase region, what's that transition called?
Bubble.
Bubble point. And vapor to liquid is dew. In a flash calculation, what you may see in a homework problem is I will say that, oh, you have some composition at some pressure and at some temperature. So for example, let's just say this is our system pressure right here. Now I can draw a horizontal line. Now this line is a line of constant pressure. This diagram is a plane of constant temperature. Now you can imagine that if I vary the temperature, the relative volatilities of these two things would change independently because they'd be a different distance away from their critical point. Vapor pressures for a pure component are exponential. So whereas methanol might look like this, pentanol may look like this. P-E-O-H? I don't know, I've never written pentanol. Right, so this diagram should be expected to change if you're going outside of the plane or inside of the plane, raising and lowering the temperature. And so really you could visualize this as a 3D phase diagram. Now, fluid phase equilibrium in thermodynamics, according to the Gibbs phase rule, doesn't tell us anything about the quantity of the phases. Material balances tell us about the quantity of the phases. Thermodynamics says they're just infinitely sized reservoirs. Right? I have an infinitely sized vapor reservoir with this composition. I have an infinitely sized liquid reservoir with this composition. They are in equilibrium. Thermodynamics helps us solve that problem. So if I have a fixed temperature, a fixed pressure, there are two solutions to Raoult's law, if this is an ideal scenario. Right? The partial fugacity of the liquid for species I is the partial fugacity for species I in the vapor phase. Now for this particular example here, this would be the partial fugacity of methanol liquid is equal to the partial fugacity of pentanol. So, my goodness, I'm slow today. Methanol vapor, and the second equation, partial fugacity of pentanol liquid is equal to the partial fugacity of pentanol vapor. The mole fractions, the mole fraction of methanol plus the mole fraction of pentanol in the liquid phase is 1. The mole fraction of methanol plus the vapor mole fraction of pentanol is equal to 1. So satisfying all of these equations will get us to these two solutions. Now, if I'm at this pressure and this temperature, there are only a finite number of compositions where I have a two-phase region. From here to here. So if I had a jar that was filled liquid and vapor for the same system at a fixed temperature and pressure, and I added methanol, let's say for example, I don't actually change the composition of my two phases. I only change how much of each of the two phases I have. Another way to think about this is exactly analogous, is if you're doing a liquid-liquid process, oil and water. If I have a container filled with oil and water, there is going to be a finite solubility of the oil in the water phase, and that's only going to be a function of the temperature and pressure. There's going to be a finite solubility of the water in the oil phase, that's only going to be a function of finite temperature and pressure. So in order to generate a phase diagram, I don't actually have to consider all of the possible conditions of temperature, all of the possible conditions of pressure, and all of the possible conditions of composition. Because there are only two lines that satisfy the multi-phase, multi-component equilibrium. So instead, we do something called a dew and a bubble calculation. The dew calculation is when I have 100% pure vapor. I calculate what the composition of the liquid phase would be. Bubble curve, I have 100% pure liquid, and I calculate what the vapor composition is going to be. That is going to be our strategy to generate these phase diagrams with the least amount of work possible. So instead of me deriving and presenting the dew and bubble curves, which I'm sure some of you might know off the top of your head, we're actually going to derive them, you're going to derive them yourselves. Because once it clicks how they're generated, then you never have to remember them again. It's relatively straightforward. So, this is going to be dew and bubble curves in vapor liquid equilibrium. Okay, we're going to treat this like it's an exam scenario. So if you read an exam question and you see the word phase, right, or what's the composition in this phase, that immediately cues you in that this is going to be a phase equilibrium calculation. So what is our starting point always going to be? Fugacity is equal, partial fugacity is equal. Now this is vapor-liquid equilibrium, so the partial fugacities across the two phases. One's going to be a liquid phase, one's going to be the vapor phase. Now we're going to generate Raoult's law. For the vapor phase for Raoult's law, we're going to make two assumptions. One, ideal gas mixture does all of it in one big lump. Ideal mixture An ideal mixture allows us to write the partial fugacity using the Lewis-Randall rule, where the partial fugacity of species I can be approximated as the mole fraction times by the pure species fugacity. Partial fugacity is going to be a function of temperature, pressure, and composition. Pure fugacity is only going to be a function of temperature and pressure. Next, if we assume that it's an ideal pure fluid, that allows us to write that the pure fluid fugacity, which would normally be a function of temperature and pressure, is in fact just equal to the system pressure. Put this together, and we can approximate the vapor partial fugacity as the mole fraction times by the system pressure. And that gives us 1/2 of Raoult's law. We're first going to assume low pressure. If it's low pressure, what does that mean we can approximate here? What does low pressure allow us to do? We'll do that in one step. Just one step before that. If it's low pressure,
So the pointing correction?
we can ignore the pointing correction. Yeah, if we ignore the Poynting correction, that means that the pure fugacity of the liquid is approximately equal to the fugacity of the saturated liquid. Now, if we further assume that it's an ideal vapor phase, or we could say it's very low pressure, then what's the next step? Well, this is the ideal gas assumption. So what does that tell us practically on how we actually calculate the fugacity?
It equals to pressure.
Yes. That means that in fact, actually, putting these two together, rather, let me just do here. This is actually specifically saying that the saturated liquid fugacity is equal to the saturation pressure. I'm trying to be very careful to make sure we identify every individual assumption. The next one is ideal mixing. What can we assume if we assume ideal mixing in the liquid phase?
The activity coefficient is equal to 1.
Exactly. The activity coefficient is equal to 1, or the excess Gibbs is equal to 0, meaning that there is no enthalpy of mixing, and the entropy of mixing is exactly ideal. So 100% random fluid orientation. That's what that means. If we put this all together, that means that the partial fugacity of species I in the liquid phase is just going to be equal to this expression. And we establish Raoult's law. Now, oftentimes, just out of habit, I'll always do this. I always put saturation pressure having a function of T, and that's just sort of from more so teaching undergraduate curriculum, because this is a reminder that the vapor pressure is a very strong function of temperature. But since this is a advanced graduate level thermodynamics class, we know that every function is a function of every other thing in thermodynamics. So this here is just sort of a convenience indication to remind us, strong function. All right, now, we'll keep this, oh geez, I want to keep all of this. I'll get rid of this part here. Bubbles easier, let's start with bubble. All right, bubble curve. Imagine we have a piston cylinder device that is at some high pressure. Right, here's our fluid. And what we're going to be doing is we're going to be lowering the pressure. The dew curve is the opposite. We're going to have a vapor, and we are going to be increasing the pressure. The composition is exactly the same in each of these two scenarios. We have 4 equations to satisfy. Here's what I'm asking. So we're going to divide this up. Let's see, the first, how many do I have? 1, 2, not quite 50-50, but close. So we're going to have the first 1, 2, 3, 4, 5. Oh, there's no easy way to divide this up. We'll just have the first 2 rows. Your job is going to be derive expressions for, let's say, the dew curve, and the back 2 rows are going to derive expressions for the bubble curve. So here is the key. What I'm asking for is we have these equations here. If I am a bubble, I'm doing the bubble curve, I have 100% pure liquid. I am depressurizing it, and I want to know the conditions when my bubbles first start to form and how I can determine what the pressure is, what the composition is at that point. The dew curve, I have the opposite. I have 100% vapor. I'm going to pressurize it, and I want to know what pressure the phase transition occurs at. Now that is going to be the solution to this system of equations, right? Assuming Raoult's law for this particular example. Right? 4 equations, 4 unknowns. We have composition of methanol in the liquid, composition of pentanol in the liquid, composition of methanol in the vapor, composition of pentanol in the vapor. 4 equations, 4 unknowns. So the tricky part about this is, which one do I substitute into which one? Do I substitute into which one? Do I substitute into which one? But the key assumption here is that the total system composition is the same across these 2 systems. So effectively what we're looking at is we're looking at a line that goes from total same composition but varying pressure. So let's see, I have some numbers calculated. Which one did I already calculate so I can tell everyone what we should start with? Let's see, a 50-50 mixture. Okay, so for a 50-50 mixture, let's say this is 50-50 here, even though it doesn't look quite like it. We're going to be solving for this point here and for this point here. Now, at the dew curve, this is going to tell me what the composition of my liquid is at the dew point. For the bubble curve, this horizontal line over here is going to tell me what my composition is of the vapor phase. So what is the key assumption that opens the door to solving this problem? We have 4 unknowns. Oops, shouldn't have erased Raoult's law. Hold on. I think everyone's got it memorized. 4 unknowns. X methanol, X pentanol, Y methanol, Y pentanol. Actually, do I have? Yeah. What's the key assumption here? I know it's a 50-50 mixture, but what can I use that information to assume?
The first bubble or the first dew will not change the composition.
That's the key. So depending on whether or not I have a dew or a bubble curve, I know one or the other compositions here. So front 2 rows, you're doing derive me an expression for pressure of the dew is equal to blank. For the back 2 rows, pressure of the bubble is equal to blank. And then I also want to know what is the composition of the new phase that forms. This is for a 50-50 mixture. You're provided the pure fluid vapor pressures, 251 and 15.3. Temperature doesn't matter. Well, it's 90, but I've already used that information to give you the vapor pressures. So, derive expressions for the pressure. And I am here to help, so shoot up your hands if you feel like you're getting stuck. But I want everyone to go through the exercise and muddle through it. Just a reminder, these are the 4 equations that we'll be modeling our way through. So I find with these derivations, the key thing is to choose the equation where you know the least amount of information, and then when you substitute everything into it, it'll all fall into place. So start with the hardest starting point that you can think of, and then work your way back.
The hardest starting point I can think of would be the routes one up there. So why we know what to do.
Who's totally lost? Someone, is anyone finished it already? Okay, so 1. You got it? So you got the dew curve? You got the bubble curve? Okay. Do you have the compositions? Oh, you guys are done. You have dew and bubble curves memorized then. So, for those of you still working on it, if I'm doing the bubble curve, I know everything about my system. I know the phase and I know the composition. What is the phase that I know nothing about?
Vapor phase.
The vapor phase. So this is going to be my starting point. I know nothing about the vapor phase. So use this as your starting point and substitute everything in. Now, if I'm in my dew curve, I know everything I need to know about my vapor phase. I know the phase and I know the composition, right? Z. I know nothing about the liquid phase, so this is going to be my starting point. And from here, there's really only screwed these up, it's backwards. Just trying to be very clear about that. All right, this should get everyone, hopefully, a boost in the right direction. Substitute this into here, solve for P, substitute this into here, solve for P, and we're done. So I'll just write this out. Bubble curve is easier. So if I write this generally, I know nothing about my vapor phase, so I can write the summation of all the mole fractions is equal to 1. I substitute in my Raoult's law. Pressure is constant across all the phases, and so from here, the pressure is equal to just the summation of the mole fractions times by the vapor pressures individually. Same thing can be done with the Dew curve. The output just looks a little bit different. Summation of the mole fractions in the liquid phase is equal to 1. Substituting in my Raoult's law. I just wrote it a little bit differently, because then you have to do a little bit of flipping around. These are equations for the bubble and the Dew curve. We can only derive them because we made an approximation. We made an approximation that when we are first starting our phase transition, the total quantity of the new phase that forms is infinitesimally small. And if we assume that that quantity is infinitesimally small, it allows us to know what the composition of one of the two phases are. And again, thermodynamics, infinite oceans. So if I take one bubble out of an infinite ocean, I feel pretty confident that I'm not significantly changing the composition. Now, next part of the question. How do I know what the composition of this new phase is?
Substitute.
So which equation is the easiest one for me to substitute in?
Raoult's law.
Raoult's law. Because in Raoult's law, let's say, for example, I'm doing the bubble curve calculation, right? So I know everything about the liquid phase, but I know nothing about the vapor phase. So in this case here, I know the liquid phase composition. I know the pure property of the species. Now I know the system pressure because I've solved for it using information that I already know, the mole fraction and the vapor pressure of the pure fluids. So the only unknown in Raoult's law is the composition of my vapor phase. Vice versa, if I'm doing the Dew curve, I know the composition of the vapor, I know the system pressure, I know the saturation pressures of the pure components, and then I can solve for the individual species. So in this case here, for a 50-50 blend, let's see, what did I do it for? I did it based on methanol. This would be at the bubble curve. The x, we know the x. We're solving for the y of the methanol. And this is just going to be equal to the mole fraction in the liquid, the vapor pressure over the system pressure. I need to give you the system pressure. If you evaluate this expression here, we get that the system pressure is 133.2 kilopascals. For the Dew curve, it was 28.8. If you crunch in the numbers for the actual, using the pure saturation species. Then the composition of methanol in the, let's see right here, in the vapor phase would be 0.943. And then at the dew curve, X of methanol is equal to 0.058. I didn't write out the equation, but it's just rearranging Raoult's law. Let's see if this makes sense, if I drew my diagram at all reasonably well. So first one here, the bubble curve, we have a 50-50 mixture, right? Bubble is all liquid transitioning to vapor. We travel down. Once we hit here, that means that I should have a very high composition of methanol in the vapor phase, and indeed I do. In this case here, it's about 95%. Now if I do the opposite, I have a 50-50 mixture of pure liquid. I draw the line over here. I should have a very low composition of methanol in the liquid phase. And indeed, I also get a similar response, about 6%. In this case, these two have some fairly large differences in relative volatility. So a flash drum like this, you're really only going to see in a chemical plant when you're separating like gases from a liquid, or something that's extremely volatile to something that's non-volatile. Anything else more advanced than that, then you're certainly going to have to use a distillation column. Questions on flash calculations? Now, one additional scenario, where's my eraser, would be in the case of a liquid-liquid system. Oh, I'm losing all of my space. Let's get rid of this one here. We don't need this. I do want to keep that. Let's get rid of this. This same concept applies for any multi-component system. Now, in liquid-liquid systems, we haven't talked about it yet, but we effectively could right now in less than 5 minutes. This is a phase equilibrium question. So if this were an exam and we had a liquid-liquid system, we would effectively just say that the fugacity of species I in phase 1 is equal to the fugacity of species I in phase 2. We no longer have the nice convenient notation of L and V because they're both liquid, and it's completely arbitrary which one you call A and which one you call B. Now, when it comes to actually substituting this in, the laws that we've learned still apply. We still have the fugacity of a vapor, or potentially we still have the fugacity of liquid. Those expressions are completely assumption-free. The fluid doesn't know what kind of phase equilibrium it's undergoing. All that we know is we know how to calculate the partial fugacity. So for low-pressure liquid-liquid equilibrium, we oftentimes write this as X of species I in phase 1 times by the activity coefficient of species I in phase 1 times by the saturation pressure of species I, which is going to be constant across both the phases. It's going to be independent of the phase, so I don't have to put a numeral. This is going to be equal to the mole fraction of the same species, but in phase 2, times by the activity coefficient of the same species, but in phase 2. And then again, the pure fluid saturation, right? All we've done here is substituted in our approximations for how rigorous we want to be to calculate the fugacity. Now, in this case, we've effectively assumed all the assumptions can be lumped here into one, which is an ideal gas vapor, right? Or low pressure. So this is low pressure liquid-liquid equilibrium. The pure fluid saturations cancel out. And our equation that we have to solve for every species in the system for liquid-liquid equilibrium simplifies down to this here. In fact, we didn't even actually have to assume that this is a low-pressure system, right? Because the pure fluid fugacities would have canceled out regardless of how pure, how ideal or non-ideal is. Now, liquid-liquid equilibrium is kind of its own beast. because activity coefficients are typically exponential functions of composition. And so for a two-component liquid-liquid system, you have to solve basically two nonlinear expressions simultaneously, whereas for the vapor-liquid equilibrium system, assuming ideal behavior, it was relatively trivial. We did it in class. So in a liquid-liquid system, a phase diagram is going to look a little bit different, but the concepts still apply true. So this is, I'll call this x of, I call it z, actually, just keep my nomenclature consistent. Z of A, and typically you're almost always going to see these as a function of temperature, but that's not entirely true. It could be different. But the phase diagrams are really just going to look like this, and there may be a dot somewhere. So, we have talked nothing at all about liquid-liquid equilibrium. Liquids can behave a little bit funky, but let's just say hypothetically this liquid behaves reasonably. I have a line. What does that line represent?
Phase boundary.
Phase boundary. So do I think that, which phase is this here? Which phase is this one? So I'm sure you've seen liquid-liquid diagrams, but just by working our way through how we know phase diagrams are calculated, let's see if we can figure this out. Yeah.
So maybe one is two liquid mixed where, one is two liquid separate.
So one's got to be a single phase and
Yes.
one's got to be two phase.
Yes.
Only one of these two makes any sense whatsoever to be the two-phase region. Which one is that?
The bottom one?
Now, why is the bottom one the only one that makes sense? Now, this diagram, if I'm varying the temperature, the pressure has to be held constant. So if I have a constant temperature and a constant pressure, that's all I need to fix my phase equilibrium. How do I draw constant temperature on this liquid-liquid phase diagram? Horizontal line. Now, if I draw a horizontal line up here, what happens?
Nothing.
Nothing. That means it's a single-phase system. So this is going to be our one phase. Now, if I draw a line down here, this is going to be my two-phase. This point right here, this is going to be the composition of fluid A in phase 1. This one here is going to be composition of fluid A in phase 2. I could switch 1 and 2. It doesn't matter. This fluid over here, fluid 2, we would call this A rich because the composition has much more A in that fluid. Phase 1 would be B rich. And that's sometimes the easier way to communicate which of the two phases you're talking about. But mathematically, I'm not going to write A rich, B rich in every single one of these ones here. I'll just do phase 1, phase 2 for the math. And then when I'm interpreting the results in my head, this is how I'll think about it. Now, liquid-liquid equilibrium is really, really annoying because activity coefficient models are very sensitive to small changes in material properties and very sensitive to small changes in composition. So this really just becomes a numerical methods annoyance. But the same concept applies. I don't want to have to solve for the phase equilibrium at every single position at every single condition. So instead, I do these flash calculations where if I had a system here at a single phase region, I dropped it down until I hit a phase transition, then I can use my governing equations to lock in that point right there. And then I do that as a bunch of different conditions, and I can effectively draw a series of 2 points until I get to, this would be called the upper consolate temperature, where the two fluids are in equilibrium. Now with polymers and liquid-liquid systems, you can get all sorts of really funky behavior. So you can have systems that are not soluble at high temperature, but are soluble at low temperature, in which case you can get a curve that looks like this. You can also get regions where you have a total enveloped phase envelope where if you heat it up, it'll go to two phase, and you continue to heat it up, it'll go back to single phase. And this is kind of the interplay between entropy and enthalpy that we're witnessing here. So they can be arbitrarily complex. So before we wrap up, I want to do 2 more special cases. actually so one special case is, let's say that I have a mixture of water and air. Or this could be any volatile solvent, right? So one of the questions that we have to remind ourselves is that if I have a glass of water at room temperature and I leave it out for a month, that water is going to evaporate. But why? Right? The boiling point of water is 100. Why is that evaporating at 25? Right? It's because it's not a single component system. A glass of water exposed to the air is a multi-component system. So if it was not for the air, the water couldn't evaporate. Now in this particular system, this is kind of a humidity calculation. But if I had air and water, and this could be any gas in water, the solubility in gas is very, very low. So I would say that the mole fraction of air in the liquid phase is approximately equal to 0, meaning that the mole fraction of water in the liquid phase is effectively 1. This simplifies my calculations for Raoult's law significantly. So that lets me know that the mole fraction of water in the vapor phase is simply just going to be equal to the mole fraction is 1, so it'd be the saturation pressure of water over the system pressure. And this effectively tells us how quickly things evaporate. So when we're talking about, this is the special case of one condensable component. One condensable component. So it's a simplification. This doesn't have to be water, it could be any fluid, but the approximation holds true. If I have a condensable fluid with a supercritical fluid, which is the case of water and air, I can assume that the air is not appreciably going to dissolve. I mean, it will, but we're talking like 10 to the minus 4 mole fraction, 10 to the minus 5 mole fraction. Not something that's ever going to significantly impact your calculations. The last thing that I didn't have a chance to get to, but we'll cover it on Monday, is when you get to a system like this, a flash calculation that has more than 2 components. 2 components, we all slowly muddled our way through the do and bubble calculations. When you have 3 to 4 components, 5 components, it actually starts to get a little bit tricky because it's not crystal clear what you substitute into which and how you interact. So I'll go over a generalized procedure to solve ideal flash calculations for an arbitrarily defined number of components. One other takeaway here is that these equations that we derived, they're universal. They're 100% universal. So if I just gave you this equation here, you didn't do anything. All that you did was substitute 100% assumption-free equations into one another. This one here is 100% generalizable. I don't have to only apply this equation at the bubble point. I don't have to only apply this equation at the dew point. What makes this the bubble curve, and what makes this the dew curve, and what makes the bubble curve, is when I substitute in Z, the total composition for the vapor composition, or when I substitute in the Z total composition for the liquid composition. But I can use this equation, if depending on the system, to solve whatever I want. That's a totally valid equation. For the 2-phase region, you can use that equation throughout. Same thing with the dew curve. It only becomes the bubble equation, it only becomes the dew equation when I assume that I know what the vapor composition is, or when I assume that I know what the liquid composition is. But if I were to tell you, right, that you're in the 2-phase region right here, both of those equations are valid. One would give you this point, one would give you that point. And that's a trick that students a lot of times get really caught up on when it comes to exams. So there may be a question that seems more complicated than it is, but you can just pull these out of your back pocket, and have them memorized, and you can solve a lot of vapor-liquid equilibrium problems, knowing that this is not unique to only one case. This is a general equation. This is a general equation. What makes it unique is the assumption. That's all I've got. All right. Thank you all. Have a good weekend, and I will see you Monday.